Good morning, everyone. Welcome to the Osher Lifelong Learning Institute at UC San Diego. My name is Joel Dimsdale, and I'm the coordinator for this morning's talk. This is part of the Medicine and Life Science series. Medicine is a bit of a mystery. We go after familiar old enemies, and sometimes we encounter new killers. And it's a quite interesting problem, striking problem, that the field has faced in recent years with a pediatric vasculitis that has grown from being absolutely invisible to being relatively common. It affects children, heart disease. It is a mystery thug, and the etiology of this remains obscure. We're privileged this morning to have a speaker, Professor Jane Burns, who has taken on this mystery. Jane got her medical training in the southern part of heaven at UNC, and then moved on and did additional training at Harvard in pediatric infectious disease and molecular virology. She moved here in 1990, where she is professor of pediatrics and director of the Kawasaki Disease Research Center. Professor Burns.
Thank you. Well, it's a pleasure to have been invited to speak here. Just a show of hands, how many people, before you saw the title of this lecture, had ever heard of Kawasaki disease? Okay, so that's really interesting. That's more than I would have thought, but yay. So I have several goals this morning. One is to share with you the excitement that we have about trying to solve mysteries in medicine. But I also want to make sure that when you leave here, that you all feel competent to diagnose Kawasaki disease in your grandchildren or great-grandchildren or your neighbor's children or cousins or extended family, because this is, in fact, a disease that lay people can recognize and diagnose. And unfortunately, it's a disease that physicians often miss. It's treatable, and when we miss the diagnosis, bad things happen. So I'm going to spend the bulk of the time talking about a new theory that we have about where Kawasaki disease comes from and what we're doing to try to solve that mystery. The Kawasaki Disease Research Center that we have here at UCSD is actually perhaps the largest group of researchers dedicated to this disease in the world. And so I hope if you're affiliated with UCSD, that makes you proud. Let's go over some ground rules, first of all, about what Kawasaki disease is for the people who hadn't heard of it before. It's what we call a vasculitis, meaning inflammation of the blood vessels. So the itis suffix is inflammation of, so this is vascular inflammation. But what makes this very different from many of the diseases that plague adults that fall in this same category of disease is that this is self-limited. And there really isn't any other of this kind of disease in medicine that is like this. And I think one of the problems in trying to solve this mystery, as humans, we're always trying to relate something that we don't know to something that we do know. And I think that urge, which has some deep psychological basis to make things something that you already know, has really worked against us, because I really do think that this disease is new. It's something that we don't know, and I think the paradigm when we ultimately figure out this disease is going to be a brand new story in medicine, which of course makes it very exciting. So it's self-limited, meaning that the disease comes and goes all on its own, and if we never treat it, it will go away on its own. But 25% of the individuals will be left with the lesion that you see here. And what you're looking at is a catheter that's been placed from the groin and threaded up to the heart, and it's now cannulating the coronary artery here. And this is the left coronary artery system, which should be about the diameter that you see here. That would be a normal coronary artery. And for those of you who haven't experienced a heart attack, this is what a heart attack is. So myocardial infarction, this is a huge blood clot that's formed here, and you don't have to be a rocket scientist to realize that the watershed muscle downstream from this is not happy and is going to die because of the lack of blood flow. So this is what happens when in pediatrics we miss the diagnosis and these children go untreated. This lesion was silent. This was a 32-year-old triathlete who was competing on the circuit, was 10 miles into his 100-mile bike ride for his training workout, all of a sudden developed terrible chest pain and keeled over on the side of the road. He didn't know that he had anything wrong with his heart. And the story goes that age 5, when he lived in Florida, he had a case of very unusual scarlet fever. Yeah, well, very unusual scarlet fever was actually Kawasaki disease. And he lived for 30 some odd years asymptomatically as a triathlete competing until this brought him down. So these lesions are silent. So if we do a bad job in pediatrics and we miss the diagnosis, this is what happens. And in fact, we did a study here in San Diego with our adult cardiology colleagues, and they showed that in a review of the regional hospitals here, including the military hospital at Balboa, that of the people under the age of 40 who have some reason to suspect that they're having chest pain due to their heart and therefore are taken to the cardiac catheterization laboratory for investigation with this catheter, that 5% of those people actually are missed Kawasaki disease patients. And that's right here in San Diego in your community. So we know that early treatment with a high dose of intravenous immunoglobulin, so I'll be using this term IVIG, and that's what that stands for, intravenous immunoglobulin, can reduce the risk of aneurysms from that 25% number down to variously 3, 5, 7, maybe even 10%. But anyway, it's clearly effective in helping a lot of our patients. So we want to recognize the disease early and we want to treat it early. And it is now the most common cause of acquired pediatric heart disease in developed countries. And we work very closely with colleagues in India. And the numbers are hard to get your arms around there, but it is suspected that it has now replaced rheumatic heart disease and rheumatic fever as the most common cause of acquired heart disease. And for sure in Egypt, where we work very closely with groups there, there's no question that among the children, this disease has now replaced rheumatic heart disease as the most common cause of acquired heart disease. So we're talking about potentially many, many hundreds of thousands of children around the world who are being affected by this, and it appears to be a new disease. So here at UCSD, I have the privilege and excitement to lead a varied group of people with projects that involve basic laboratory research and also clinical research. So I won't be talking about these individual projects so much today. We'll be focusing more on the climate project here, but we have a number of initiatives that are designed to improve the life of our patient, to improve the treatments. And one very important objective that we have is that IVIG is extremely expensive, and we need to understand how it works so we can replace it, because the majority of the children in the world who are affected by this disease live in resource-challenged environments where they will never be able to afford this. So this is our gang here at UCSD. We have foreign scholars from other parts of the world who come here to study, and then we send them back to their countries so they can take the learning back there. And I want to particularly point out my colleague, Audrey Tremolay, who is our clinical trialist and runs all of our clinical trials in the children, and those all happen at Rady Children's Hospital. So this is your lesson in becoming a diagnostician for Kawasaki disease. And I hope you'll take this to heart. that you really can recognize and diagnose this disease. And who knows whose life you may save. So what you want to look for is high fever that is often very difficult to control. So fever is where it all starts. And then over the course of the first week, the children develop most of these signs. So the bloodshot eyes are very characteristic. They're not weepy or goopy like pink eye. They're just a dry eye. Both eyes look the same, that bloodshot appearance. The swollen hands and feet, you can see there, and these hands are very painful. So they, a toddler wouldn't want to hold his bottle or would refuse to walk. About a third of the patients develop this very large lymph node. That's that big mass that you see on the side of the neck. And that can often be misdiagnosed as a bacterial infection. So we get a lot of mistakes made where the children are treated with antibiotics because they think that this represents a bacterial infection. And it does not. This will all go away with treatment with IVIG and no antibiotics. And here you can see the lips of this child here and the lips here. It's very dramatic, the changes in the lips. It's not just a little chap because they have fever. It's really this redness and the fissuring and bleeding of the lips. And the tongue gets this denuded appearance. A normal tongue has all this gray part to it. And there's actually an injury on the surface of the tongue where all of that gray part has sloughed off. And you're left with this appearance that we call the strawberry tongue. And then there's swelling of the feet and this rash that can be all kinds of forms. So the specific nature of the rash doesn't help us very much. It doesn't help us to biopsy it. There's nothing to see there. But it's a very common clinical sign that accompanies the disease. So the clinical definition of this disease is fever for at least 5 days with 4 out of the 5 of these signs that you see here. So you are now all certified and competent to make the diagnosis when you go to, your holiday get-together with family members. And I empower you to make that diagnosis. So if we don't make the diagnosis, and even sometimes if we do make the diagnosis, and even in a timely manner, the genetics are against us, and a subset of these children will go on to develop these aneurysms. And so that's what you're looking at with the yellow arrows here. This is a reconstructed CT angiogram done at Rady Children's Hospital in one of my patients. And again, the normal diameter of this vessel should be about like this, and you can see this huge bulging. And clearly, the flow of the blood through this structure is not going to be normal, and they're at huge risk for a clot forming. And that's what the heart attack risk is. The other risk is you can see a little bit of calcium here. This is a different way of looking at this vessel, but the same vessel. And the outlet of these aneurysms here is where scar tissue can build up. And so even in the absence of a clot forming in the aneurysm itself, this outlet becomes obstructed and can lead to a heart attack. And in this unfortunate young man, we have aneurysms on both sides. So the heart has been subtracted away here. It would be here. This is the aorta, the major blood vessel that takes the oxygenated blood away from the heart. And here are the coronary arteries coming off here. And clearly very, very abnormal and very at risk for clot formation. This young man is currently in college and doing well, but he has to take medication, systemic anticoagulation, similar to anybody in the audience who has atrial fibrillation. It would be the same kind of medication. And this is the autopsy specimen from the young infant who actually inspired my career to continue to work on this disease in 1979. This is her heart. She was 3 months old. This is her heart here. These are her lungs. And here are the beaded aneurysms on the surface of her heart. These are the aneurysms here and here. So the treatment, I was fortunate to be part of the 1984 clinical trial that showed that a high dose of this intravenous immunoglobulin could reverse the immune damaging effects on the heart and protect the heart and prevent aneurysms. And I enrolled the first patient in a national clinical trial that was funded by your tax dollars, thank you, by the NIH on Valentine's Day 1984. And it was one of the fastest, in fact, this was brought before Congress. They paraded it out every year when appropriations time came around, because it really was one of the great success stories of clinical research for pediatrics in the modern era, that we were able to show in a very short period of time. In fact, the trial was stopped prematurely by our Data Safety Monitoring Board because we were randomizing children to either receive this treatment or aspirin alone, and it was so effective that they said, you have to stop, everybody needs to be treated with this. And the article was published in the New England Journal as the lead article in 1986. So to go from the first patient enrolled in 1984 to a national change in the recommendations for all children, and this became the medical legal precedent. So if you didn't treat with IVIG, you were likely to get sued. So the lawyers took care of that. And it was dramatic, and it was a wonderful thing. It was not an original idea, truth in advertising here. So the Japanese did it first, but they didn't have a tradition in Japan of the classic randomized placebo-controlled clinical trial that we think is the gold standard in this country. So they had treated a number of patients and shown what they thought was a dramatic beneficial effect, but it really fell to the taxpayers of the United States to prove that that was true. So we also give it with aspirin. Most of you probably know that we don't use aspirin because of the complication of Reye syndrome that happens in the presence of a couple of different viruses, the influenza virus or the chickenpox virus. This is the only disease in pediatrics where we actually use aspirin. And maybe we don't need to use it, but at the time it was the only thing that these children were treated with, and so we're sort of stuck with that. We use the low dose. Many of you may take one baby aspirin tablet a day. And the reason for that is just to grease your platelets, the cells that are responsible for forming blood clots, to just grease those platelets a little bit. And we do that for our children as well. So the problem is, as I said, recognizing these children. So you've all been trained now to recognize Kawasaki disease. And there are various features of these other children, various children. Only this one has Kawasaki disease. So it can be subtle, and it does require some training to sort it out from the other rash fever illnesses in childhood, but this is the only one who has KD. I've just come back from Japan, where I was speaking at the 38th All Japan Kawasaki Disease Conference. I have great shame in that I do not speak Japanese, even though I've been working on a Japanese disease. I actually enrolled in an extension course here at UCSD, and it made it to the first two classes, and then it all fell apart. So good for you all for being here. I just couldn't sustain it and work full time. But anyway, the numbers are not good from Japan. The attack rate, depending on if you look at 2015 or 2016, is around 350 cases per 100,000 children less than 5 years of age. This is a toddler age group disease. In 2015, they had over 16,000 cases despite a falling birth rate. And this means that one in every, it's probably higher than this now, but at the time that these calculations were done, it was 1 in every 60 boys and 1 in every 75 girls will get Kawasaki disease during the first 10 years of their life. So a very significant disease, more common than autism in this country. And these are the data that were presented a couple of weeks ago in Japan that are unpublished. And it's interesting that there's been a change in the slope of this curve. So a couple of historical points to make here. If you look back to 1961 was actually the day that, the year that Dr. Kawasaki, after whom the disease is named, saw his first case that he recognized as something new that had never been seen before in Japan. And a national survey was done in Japan in 1970 where they found 10 children who had died of heart attacks, which are extremely rare outside of Kawasaki disease. And so that was when, for the first time, the heart disease and the clinical illness were put together. And you can see there were these very dramatic nationwide epidemics. And this was really terrifying because this was a new disease in Japan with this huge spike here in number of cases. And there were about 16,000, 15,000 cases in that epidemic. But you can see that the attack rate has just continued to rise with a sharp increase around 2000, where the slope has really changed and it's gone up. And interestingly, there have been 2 times when there's been a decrease in the number of cases. So it was in the 2008, 2009, and just recently in the latest evaluation. The Japanese do this nationwide questionnaire survey, and that's how these data are collected. So that has to be a clue, right? If you're Sherlock Holmes, you look for the anomalies. You look for the things that don't follow the pattern that you expect. So what happened that was different in 2008, 2009, and then in 2016? I'm waiting for you to tell me the answer. So this is Dr. Kawasaki and a younger me doing, in 1998, there are actually a couple of wonderful videos of Dr. Kawasaki. This was a 1998 expedition that we had to Japan that was funded by the National Library of Medicine. Those days are gone. But at that time, the National Library of Medicine funded us to do a project called Living History, because all of the people who had described this new disease were still alive. And we went and we did interviews all over the United States, all over Japan, in the Philippines, and in India. And you can see those videos. One's called Race for the Answer, and the other one's called The Eyes Cannot See What the Mind Does Not Know. And those are on YouTube. So you can enjoy hearing from Dr. Kawasaki about the description of his disease. Race for the Answer is what it's called. And again, that was funded by the National Library of Medicine. And we have the archive sitting in my office waiting for Discovery Channel or somebody to want to make a movie out of it. So I wish I could tell you how many patients there are in the United States each year, but you know the cuts to our public health service, the CDC, and there is not enough money to do any kind of active surveillance for this disease. So we don't know. You can use administrative databases, which are run by the insurance companies, where they're very interested in charges and billing, and so you can look at those numbers, and it would suggest from those data that maybe we're around 5,000 or 6,000 cases a year compared to 16,000. But I'll tell you, the data that we have in San Diego County, where we do prospective, active, and complete surveillance, would suggest that the numbers are much bigger, or that cases are being missed all over the United States and deflating that number. So our population base here is something north of 3 million. And this is what it looks like at Rady Children's Hospital. So this is just raw number of patients. And we've got 2016 here. And I think you can see that we have a suggestion of an overall increase. This slope isn't statistically significant, but it certainly feels like the number of patients are increasing because there are only 2 of us who take care of all these patients, and it just seems like we're getting much, much busier. We follow about 1,700 families in our Kawasaki disease clinic. So the attack rate here, as compared to 350 per 100,000, less than 5 in Japan, is probably about 25 cases per 100,000, 100, something north of 100 new cases per year. And that would translate, this is a rough calculation, to 1 in every 2,000 children developing the disease in our community. There's a very important genetic predisposition to this disease. And although I showed you raw numbers there, here I'm showing you number of cases per 100,000 children less than 5 of each different ethnicity. And so you can see that Asians are way overrepresented in the green here. So Asians in almost any year that you pick are overrepresented. African Americans are also overrepresented. And in the United States, the hospital system that actually cares for the largest number every year of Kawasaki disease patients is in Atlanta. The Emory system, which involves 4 different hospitals, they basically serve the entire state of Georgia, and almost all of their patients are African American. So this is our proposed paradigm for how Kawasaki disease operates, an important genetic predisposition, that's a bad sign to get paged in the middle of the lecture, and an environmental okay, there you go. So new Kawasaki disease patient at Rady Children's Hospital as we speak. So genetically susceptible hosts. And we think that the environmental trigger is something that we're breathing in that's very widespread in the environment, and everybody's being exposed, but only few are chosen to get this disease. So we're going to spend the rest of the time really talking about the environmental trigger. I was trained in molecular virology, and I really wanted this to be a virus because I knew a lot about viruses, and I was really skilled to work with viruses, and darn it, you know, I just don't think it's not only is it not a virus, I don't think it's an infectious agent. And, you know, they barely invented immunology when I went to medical school. So it's been a lot of on-the-job training and, you know, continuous learning, just like you're doing, for me to get up to speed on the immunologic and genetic mechanisms that could be underlying this disease. But I don't think it's something we're ever going to be able to treat with antibiotics or antivirals or antifungal agents. I don't think it's alive. I think it's a piece, perhaps, of a living thing that the children inhale, but I don't think it's alive. So we work very closely with teams in Japan, and we did an analysis with Dan Kahan at Scripps Institution of Oceanography, and I never thought when I went to medical school that I'd be hanging out with climate scientists, but that's what's wonderful about this profession and why it's such a privilege, because I get to hang out with all kinds of people who are infinitely smarter and know about all kinds of magical things that I know nothing about, so lifelong learning again. And we did an analysis of the Japanese cases that they shared with us, and we determined the average incidence, meaning the number of cases per day for each month in each prefecture. And then we made a color-coded map that I'll show you here. So focus on the map over on the left-hand side of your screen first. This was the first map that we made, and we published this back in 2005. What you're looking at is the archipelago of Japan, and it's color-coded, so when they're higher than the average number of cases for that prefecture, it looks red, and when they're lower, then it looks blue. And we start in January, and we go to December. So when we first published this was really our analysis of the Japanese data, but it was the first time that we really brought attention and shone a light on the fact that this is a very, very seasonal disease. And so you can see in January, it was very hot. Then the pattern goes cool again, and then you see there's a second blip in the summer. Now focus on our recent, this is unpublished, we just completed this map, using the next period of time, 2001 to 2014, and look at what's happened to the seasonality. It's becoming exaggerated, right? So the low months of the fall, where if any of you have traveled in Japan, you know that it's the most delightful time to be there. There's low humidity, the weather's beautiful, it's not so rainy, you're outside all the time, it's really lovely. So September, October, November, very low number of cases. And look what's happened to January and December. It's just like, it's like a volcano. I mean, it's just exploding. So whatever is causing this disease, whatever is traveling in the air, is becoming cast in stone in terms of its seasonal variation. So we've teamed up with a number of climate scientists in Japan, and this is Atsushi Matsuki, who runs the climate station. So what Atsushi did, so first of all, he's at the climate center that is on the Noto Peninsula right here. And he wanted to look at whether there was any pattern of the way the disease spread across the country, but the whole country is going like this together. So it's not like a spread, like an epidemic spread of influenza where we would see a concentric circle of cases spreading out. It's the whole country. So what that means to a climate scientist is that there is something acting across a very broad swath of geography. And basically the only thing that does that is the wind. And that wind apparently also blows over Korea, because the numbers and the seasonality for Korea from published data from their government matches. Obviously, this is South Korea. North Korea also happens to be in the path of the wind, but not surprisingly, we have no data from North Korea. So this trigger seems to be associated with large-scale environmental factors, and Korea and Japan are working together. So we undertook to call in all our favors to friends across the planet, and this is global research, to try to understand the seasonality of Kawasaki disease. And we managed to call in favors from 40 different locations, 25 countries, and the color coding of the dots here shows you the number of cases that were in the time series that were contributed to us. So you can see that our sampling is just blue and green dots for the southern hemisphere. So we really had inadequate data sets from them. And the other thing that's important to know, I did not know this until I started hanging out with climate scientists, is that wind does not cross the equator. So our circulation in the northern hemisphere and the circulation in the southern hemisphere are never connected. So we had more data from the northern hemisphere, and cut to the chase here, this is what we found, that there's a coherent seasonality of Kawasaki disease throughout the northern hemisphere, and that the month of maximum KD in the northern hemisphere was January to March, and the month of minimum Kawasaki disease was concentrated in the late summer and fall months, as you saw for Japan. So we extended our climate team to include the group from Barcelona, Xevi Rodo and his group, and this is really the work of Dr. Rodo, who is a climate scientist at the IC3 Climate Center in Catalonia. And this is his aha moment that was published in scientific reports. What he did was, he was on sabbatical here, so let's hear it for sabbaticals, right? These are very useful and good things to give smart people a chance to just think quietly without a lot of administrative and other teaching responsibilities, just to be able to think. And Xevi came over here and discovered the work that we were doing on Kawasaki disease. He'd never heard of it before, and just became intrigued, like everybody who works on this disease. We got a hook in them, and then we just bring them in. And so Xevi became fascinated by this. He has small children. He had skin in the game. And he began trying to model the anomalies. So, you know, in the hard sciences, no, in the medical sciences, we do experiments where we have controls. So in climate science, you don't manipulate the climate, right? The climate is, and you're trying to study patterns. So what climate scientists do is they focus on the anomalies, and the anomalies are where they go for their clues. And then they make hypotheses based on the anomalous events, and then they see if it applies to the more regular events. So he focused on those epidemics there. And when he tried to model all of the various climate features like temperature, dew point, precipitation, yada, yada, the thing that leapt out of the computer at him was the directionality of the wind, which is what you see for the 1982 and the 1986 epidemics here, that there was a very strong wind, anomalously strong in those years, that blew from the Asian landmass across Japan. And at the downturn of the epidemic, as the cases began to wane, the wind completely reversed and blew from the Pacific, going back up in a north-westerly direction. And that's what you see in the small inset there with those vector lines. So this was his aha moment, and he tested this in various ways that I won't go into statistically, and it held up and it survived peer review and was published. So we're talking about winds that basically travel in the troposphere, in the mid-troposphere. So not necessarily the wind that you feel on your face walking outside this building, but winds that are more up towards the jet stream where you would be in an airplane. So is there a precedence for long-range transport of some disease-causing agent that could travel, let's say, on an aerosolized particle? Well, this is a scanning electron micrograph of what an aerosol particle looks like. So, you think of dust particles in the air as being little round balls. Well, they're obviously not. They have nooks and crannies and all kinds of spaces where things could be hidden and carried. And in fact, there's a great precedent about the dust storms from the Sahara, shown here in this NOAA video, that travel all the way across the Atlantic Ocean. When they hit the warmer temperatures of the Caribbean, the wind slows down, and now they deposit their dust payload into the Caribbean waters, and they deposit an Aspergillus, a fungal species. It's not a human pathogen, but it's obviously very pathogenic to the fan coral. And if you are an avid snorkeler, you know that the fan coral is very threatened in the Caribbean, and it's dying out because of this pathogen that's being transported on dust from the Sahara all the way across the Atlantic, falls into the ocean, sporulates, and kills this target organism. So it's an example. It's not a human example, but it's an example. And Chevy went on to do more work on this, where he actually did what's called back tracing of the wind. And this uses amazing satellite data and mathematical techniques that I don't know how to do, and a lot of huge computing. But with this big data analysis, he was able to back trace the wind and show that the surface wind patterns that were associated with the increases in KD cases in Japan, that the source of that wind, the particles carried by that wind, was the region of northeastern China. And so we hooked up with Hirosho Tanimoto, who's the very young and energetic chief of the National Institutes of Environmental Sciences for Japan. And he lent us his research aircraft, which is shown here, that has a manifold in it that the plane can fly along, and the manifold is open, and dust or aerosols can be filtered into the plane and then trapped on a quartz filter with a big air sucking machine, basically, which took up the entire space. There was room for one engineer and the pilot, and the rest of it was this giant vacuum cleaner, basically, for the wind. And the plane flew on a course that was actually being dictated by the climate scientists in Barcelona, who were in contact with the pilot, and they were directing the plane to fly directly into the wind that they felt was coming from the putative source region in China. And they collected the filters, which were then handled very carefully so as not to reverse contaminate them, because we didn't want to know what was on the countertop in Japan. We wanted to know what was on the filter. And then they were analyzed by Ian Lipkin's lab at Columbia University. So Professor Lipkin is one of the world's experts on new pathogen discovery. He has a lab that is specialized in avoiding contamination from the environment. So when you're working with samples where you really want to know what's in the sample at the molecular level, this is a non-trivial exercise. It's easy if you just need things sterile, but we're talking about molecularly sterile. And Ian's a great friend and colleague. This is our third time to try to figure out the cause of Kawasaki disease. We've worked together for about 30 years. So he was on it. And what he found, and we are pursuing this hypothesis, was that from the air, the flight filter, there was an unusual appearance of Candida. These are yeast. And when we compared it to the surface microbiome for fungi, we found nothing there. So I got a high school student to start working on this, because sometimes when you want to think outside the box, you need people who can think outside the box, and we're sort of too much in the box. So this is actually the brother of one of my Kawasaki disease patients. And he's a genius. He's on a full scholarship now at USC, where they're paying him to go to college there. So he's earning a lot of money doing artificial intelligence, and he's actually working on perfecting the computer diagnostic tests that we're developing for Kawasaki disease. And he's 16 years old. So Peter went off to the library and started reading microfiche to try to understand what could be carried in the wind. And we realized that at the time of year when the epidemic is peaking in Japan, this is what the source region looks like. Okay, this is Harbin and the dramatic ice palace. This is from a piece that was in the New York Times Magazine section, but you know, it's a big tourist destination. It's minus 26 degrees Fahrenheit is the average temperature in this place. So it's not like people are out tilling the land or, you know, doing something like that at the time when there's this major epidemic. But I suggested to Peter that he might focus on what was being burned, because it seemed to me that if you live in a place like this, you're burning things to stay warm. And in fact, he came across this news brief from Harbin in an English language literature describing sunflower biomass fuels to power boilers for oil extraction. And he then went on to investigate further what happens with biomass fuels. Now, biomass fuels are something new after World War II. And remember, that's one of the clues that I've given you, that this is a new disease and it's new after World War II. At least new in Asia. We won't get into the Western Hemisphere, so we'll just talk about Asia. So this study was done in the EU to look at dust emissions and the output of various kinds of fuel. So this is looking at multi-fuel domestic boiler as a function of the pellet type. Okay, so you can make biomass fuel pellets out of all kinds of things, but it turns out they grow a lot of sunflowers in this region in China, and you need a lot of oil for cooking. They also grow a lot of maize, corn, and you need a lot of oil for Chinese cooking. And so there's a huge industry in this part of China to crush the kernels of corn or the sunflower seeds to extract oil, and to power those boilers and now actually power plants just to generate heat. They're using these biomass fuel pellets. And you can see that the sunflower husk pellet creates a huge amount of ash, more than any other of the products. And then Peter made this graph. This is all his work, age 16, where you have the first boiler plant opened right prior to the onset of the first epidemic in Japan. Now, I understand the problem of association studies. Like, I could put up coffee consumption, you know, and many, many things. I mean, many things can be associated, and obviously association does not prove causality. This is another graph that Peter made of maize production in China versus KD cases in Japan. So the cases in Japan in blue, and the maize colored is the corn production. So, okay, this is just an association. It doesn't mean causality, but maybe it's a clue that we could pursue. And this is what's happening with biomass fuel plants, power plants to generate electricity and generate heat in China. It's being used in lieu of fossil fuels, because fossil fuels, when you burn them, create all kinds of toxins and bad pollution. This creates a lot of ash, but it's fairly non-toxic in terms of the nitric oxide and the sulfur dioxide and the other noxious things that come from burning fossil fuels. So one could argue that it's better for the environment, although it creates a lot of ash. It may be worse for Kawasaki disease. So the hypothesis that, again, this is Peter, age 16, fungi are abundant on maize husks and sunflower seed hulls. The cell wall components of fungi are thermally stable up to 160 degrees. The sunflower boilers do not exceed 120 degrees, and emissions carrying fungal antigens from biomass fuel plants and boilers are inhaled by genetically susceptible children and trigger KD. All right, so if age 16, Peter turns out to be right, yay. We're working again with Atsushi Matsuki at the Noto Peninsula Climate Station. And this is a little sneak preview of a paper that we're working very hard to try to pull together so we can get it submitted. And this is describing our local climate team, so Mark Thiemens, Dan Kahan at Scripps Institution of Oceanography, Jen Burney here in always forget the name of her department, but it's something about like politics and the environment, but it has a better name than that. Anyway, all of this amazing group of people, this is their nights and weekends project. We have no grant that is funding this. This is literally what we do on our weekends. And I want to share with you this analysis. So this is unpublished, unvetted. You're hearing it first here in this room. And I hope my Christmas present will be if we can get this manuscript out before Christmas. And we're planning on sending it to a high-impact journal. And so let's just look at these panels. This top panel here is an analysis that was done, and we're working with a team from Norway as well. So we have Zoom conferences every Tuesday with Norway. So it's amazing what you can do these days with video conferencing. So the Norwegians have particular skills in doing a lot of big data analysis, and they have the data set from San Diego County. And what they've shown is that there is a non-random distribution of our patients. And what they've proved is that there is both temporal clustering and spatial clustering. So the temporal clustering is in panel A. Those lines are through the cluster, represent clusters of cases. And you can see that the cases are not evenly distributed throughout the year. There's a seasonality, but this is actually detrended for seasonality and showing, in addition to seasonality, there is this temporal clustering of cases. In panel B, what you're looking at is the excess NOx statistic. Okay, I'm not explaining that to you because I can't, but it's basically a statistical method of saying there's one case here. What is the probability that the next case that occurs in San Diego County will be at some given distance from that first case? So one case, where does the second case live? So we have geospatial GPS coordinates for every one of our patients, for their residents. So they took this data set of 1,200 patients. Our data people got the GPS coordinates for every single one of those patients. And then they simply ran this program that asks, are these patients randomly distributed throughout this geographic area, or is there a suggestion of clustering? And where you see the X's that are circled in red, those are the statistically significant, meaning if you did a Monte Carlo distribution, if you took those same 1,200 patients and you sprayed it over our county and you did that 10,000 times or 100,000 times, would you, in any of those random distributions, end up with the distribution that we actually see? And the answer is no. So the distance is about 15 to 25 kilometers. So again, it's not in the kind of space that you would see with influenza, where it's the person who lives next door who gets it, right? But it's the person who lives kind of 3 blocks from you, right? Or, you know, just nearby, but not way far away. And that was statistically significant. So it's clustering in time and space. In C, what you see is the work of our oceanography team looking at whether there are anomalous climate features that are associated with these clusters. And when they look at the clusters, so they can look at days that have clusters or periods of time that have clusters and period of time when there are no KD clusters, and then compare those. And so what you're looking at there is the 700 millibar height pressure map over the mid-Pacific and the Aleutian region. And the black boxes in that area mean that it is highly, highly anomalous. So there is a high pressure thing sitting out there in the mid-Pacific and in the Aleutian distribution that is associated with KD cases. And what does 700 millibar high pressure mean? It affects the wind. And then down here in the lower panel D, you see our county down in the very bottom there along the Mexican border. And when we compare days when there are clusters of cases versus days where there are no clusters, the temperature is highly anomalous, and it is warmer on those days. Okay. So I'm going to leave you with those thoughts. And I'd be happy to take questions. Thank you.
Let's take 10 minutes.